Welcome to our next unit on gas laws. This is a good one. It's pretty easy. It makes sense. We've all heard of gas before. So I think if you had to take the gas test right now, you wouldn't get 0. I think you'd get some questions right. For example, we know the arrangement of gas particles. They're far apart. They have lots of energy. They're bouncing all over the place. So in general, gases would have low density. If density is a measure of mass per volume, and if I compare a gas to maybe a liquid or a solid, there would be less particles in a given volume, meaning less mass in a given volume. So maybe, I don't know, like here's my area, and I try to section off about the same volume. And obviously this is a solid and liquid and gas. I can tell that there's less particles in that same volume of a gas versus a liquid or a solid. Less particles, less mass. Gases are low density. Gases are highly compressible. Because there's so much space in between the particles, we can apply pressure and compress those gases. So here, maybe this is like a movable piston or like a syringe. Or if I push down on this piston and I apply pressure, I can compress those particles into a smaller volume because there is so much space in between the particles. Gases take on the complete volume and shape of their container. So if I have gas in one compartment and I open a valve in the middle, the gas particles will completely fill the entire volume of the container. And finally, because gas particles are constantly moving and colliding with the walls of their container, gas particles create substantial pressure. And whenever we talk about the pressure of a gas, we're talking about the collisions. If I'm doing something that causes more collisions, I will increase the pressure. Okay, so I bet you would have gotten some of those right. General properties of a gas. All right, so moving on, we want to look at something in this video called the kinetic molecular theory. These are statements that describe how we think gases should behave under what we call standard conditions. Okay, well, number one, this is the kinetic molecular theory, which means that at the time these statements were put on paper, were derived, they seemed to make sense at the time. Based on the data that scientists were familiar with at the time, these force statements seemed pretty legit. Now today there are a few that maybe need to be tweaked because obviously as time goes on we have more sophisticated lab equipment and we can collect more sophisticated lab data. So this kinetic molecular theory describes what we call gases under standard temperature and pressure. We call these ideal conditions. Ideal conditions aren't necessarily like lab conditions. I know it's called standard temperature and pressure, but look at standard temperature. Standard temperature, 0 degrees Celsius or 273 Kelvin. I'm pretty sure that we don't do labs at 0 degrees Celsius. Like the freezing point of water? No. Usually we're so used to using Fahrenheit, but like in the 20s, 20 to 25 degrees Celsius is probably like room temperature. So we're going to need to correct for that. When we do labs and collect data, we are not collecting gas data at standard temperature. Standard pressure could be any of these. These are just some common units used to measure pressure. 1 atmosphere is standard pressure. That's kind of like the English unit of pressure, equivalent to like the feet and inches. 1 atmosphere is standard. About 101.3 kilopascal, or 760 millimeters mercury. Those are maybe like some metric units that we use to measure pressure. The 760 millimeters mercury is measured with what we call a barometer. We used to have one, but it's seriously a giant tube filled with mercury. And then you just read the level of the mercury in millimeters. Yeah, we can't have that anymore. There's no mercury allowed in schools. So we can use the unit millimeters mercury, but we're just not going to measure with a mercury barometer. Equivalent would be 760 torr. You might run into this unit at some point. They are equivalent. A man named Torricelli was the one that came up with this concept of a barometer, where the level of the mercury would rise or fall depending on the atmospheric pressure. 760 torr is another acceptable pressure unit. They're all equivalent to each other, and they're all standard, and they actually do kind of match lab conditions. We'll use some pressure sensors in the lab. The lab should end up having like an atmospheric pressure of about 101 kilopascal. So these conditions are known as standard temperature and pressure. Sometimes you'll see STP. They'll say, I have a gas at STP, referring to standard temperature and pressure. Then these would be the conditions. 0 degrees Celsius, 273 Kelvin, or any of those pressure units would be standard. All right, so here are the 4 postulates or statements of the kinetic molecular theory on gas behavior. Statement 1, gas particles are so small that if all the gas particles in a given volume of a gas were condensed, the total volume would be 0. Now, to clarify, they're saying like the total volume of the particles themselves would be 0. Oh, brother. Okay, so let's say these gas particles are in a container. I don't know, some kind of a box. And obviously gas particles are always moving and they're far apart from each other, so there may not be as many gas particles in this container as if I filled it with a liquid or a solid. So here's my container, here's my gas particles. This statement is saying that if all the gas particles in this container were condensed, they're all smushed together as close as I could compact them, the volume of the particles would be so small that we'd call it 0. The volume occupied by the particles themselves would be 0. If I took all of these gas particles and I condensed them, so maybe they would just occupy like a tiny little portion of the container. Maybe that would be like all the particles once they're condensed and smushed together. Okay, well that's a little funky. I have one issue with this statement, and my issue is with the word 0. Would they really be 0 volume? Isn't that like a requirement of matter? That all matter has mass and volume? It takes up space? How can you say that if I condense all these particles, I smush them all together in a tiny little ball, that the volume would be 0? Aha, I don't like that. So maybe at the time, scientists thought that, whoa, the volume is 0. But now that we have more sophisticated laboratory equipment, it would be more accurate to say that the volume of the particles would be too small to measure. It's not that the volume is zero. If I take all those little blue gas particles and I smush them together and I condense them as close as I can possibly compact them, the volume wouldn't be zero, but it might be too small to measure. So it might appear that there's no particles in this container. Because even though I might condense them from the gas phase to the liquid phase to the solid phase, the gas particles initially were just really far apart, so there weren't that many gas particles in the container to start with. Even if I condense 1,000 or 1,000,000 gas particles, they're that tiny that I might not have measurable volume. So what they want you to get from this statement is really just that gas particles are so small. I mean, any particle for that matter. Atoms and molecules are so small, and gas particles are so far apart that even though I may have 1,000, I could have 1,000,000 gas particles in a container. I could condense them together, and I really might not have any measurable volume. Particles are small, and they're far apart. Statement 2, I'm actually fine with this one. Gas particles are in constant random motion. Yes, they are. They're always moving, and their movement is random, so they could bounce off the ceiling, off the floor, off each other. We can't really plan the trajectory of a gas particle, but I can bank on the fact that they are constantly moving. I'm fine with statement 2. Statement 3. Gas particles are not attracted or repelled by any other gas particles. Okay, for the most part, sure. For the most part, I'm okay with this because, I'm going to add in my little disclaimer, gas particles are not attracted or repelled by other gas particles because they are far apart. And usually gas particles are pretty far apart from one another, so sure. Often there are no significant attractive or repulsive forces between gas particles. However, we cannot always say that there are never attractive or repulsive forces between gas particles. Okay, so here's my other disclaimer. However, intermolecular forces, oh my goodness. Intermolecular forces do exist. They're just really weak. We know that the attractive forces between gas particles are often weak because they're far apart from one another. But we can't say that there's never any kind of attractive or repulsive force between gas particles. They're just usually not significant because the particles are so far apart. But what if, let's say I have water molecules. So here's a water molecule, a little upside down Mickey Mouse. And let's say here's another one. Adorable. And this is the oxygen and the hydrogen. Oxygen and the hydrogen. Okay, so let's say I have water. Water can be in the gas phase, and we know that water molecules are polar, meaning that the oxygen end is partially negative and the hydrogen end is partially positive. The oxygen is negative, the hydrogen is positive. It's a polar molecule. The bonds between the hydrogen and oxygen are very polar, and they're not arranged evenly around that center oxygen. Usually, this is not a big deal because water vapor has molecules that are pretty far apart. But let's say that maybe by random chance these particles are kind of in the same area. Well, then could there be some attraction between like this positive hydrogen and the negative oxygen? Of course there could be some attractive forces. They're just not usually significant until I make those particles a little bit closer together. So what we're going to find later on is like, what if I decrease the volume? What if I put water vapor in a really small container? Well, now there might be some more significant attractive forces than if they were in a large container, because now I'm kind of forcing those particles to be a little bit closer to each other. Oh. I know along the same lines, there could also be repulsive forces. If two water molecules are kind of moving in the same place at the same time, and they happen to be located next to each other, so that like the negative oxygen on one molecule is kind of close to the negative oxygen of another molecule, well, sure, there could be some repulsive forces. There's always intermolecular attractions. But in the gas phase, they're usually not significant because the particles are far apart. So there's my disclaimer on number 3. 4, I'm actually fine with. Kinetic energy of gas particles is directly proportional to their temperature. We know that. So this might be at like a low temperature, where the gas particles are moving and they're just kind of bouncing around. But at a high temperature, the particles have way more kinetic energy, which means there should be more movement and more collisions. So you probably know that, like if you increase the temperature, you increase the pressure on a gas. Sometimes that might not be a good thing. I mean, if you have like a, I don't know, if you put a closed container of gas in a hot environment, the pressure can eventually be so great that the closed container bursts. Well, now we can explain that in terms of particle behavior. On a higher temperature, the particles have more kinetic energy, which means more collisions. More collisions means more pressure. If the pressure becomes too great, your container might not be able to contain that pressure. And you could have a small explosion. That might not be good. Don't try that. All right, cool. So this last question down here says, do real gases always follow these postulates? No. Boop, 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 no. Here's the differences. Real gases do have volume. And the particles themselves have to have volume. It's just insignificant. So if I say that I have like a 1 liter container and it's filled with gas, well, technically some of that 1 liter volume is occupied by the gas particles themselves. But the volume occupied by the gas particles themselves is so small that we essentially say we have 1 liter available to the gas particles. We don't even consider that some of the space is occupied by the particles themselves. It's so small. They really have volume and intermolecular forces. Cool. They're just usually not significant unless you change the conditions on the gas such that now those particles are kind of close to one another. Now we might have to take into consideration any attractive or repulsive forces that might occur between particles, even in the gas phase.